Okay, so so we have this partition problem where we're given a set, okay, and we want to find a subset such that everything in that subset sums to everything that is not in that subset. So we want to partition this set into two equally summing subsets. Okay, that's the partition problem. In the bin packing problem, we're given some numbers between 0 and 1, and our goal is to divide them up into k containers such that the sum of every container is no more than 1. Okay, so in bin packing, we're given some like weights, and we want to divide them up into, we want to see whether or not we can divide them up into k boxes such that none of the, like every element is in exactly one box. So no element is in multiple boxes, and every element is in one of the boxes, and no box exceeds the capacity of 1. Okay, so suppose we're given that partition is NP complete. Our goal is to show that bin packing is NP complete. Okay, so in particular, we want to prove that the specific example where we only have 2 bins is NP complete. So what do we need to show that bin packing optimization is NP complete? What are the 2 things we need to show? Anyone remember? Yeah, right. So but what is the first thing we need to show actually? I mean, this thing that we usually show first because it tends to be easier. We want to show that it's in NP to begin with, right? So we have to show that it's efficiently verifiable. And then we show a reduction. Do we show the reduction from partition to bin packing or from bin packing to partition? Exactly. It's partition to bin packing because we know partition is NP hard. And so if partition reduces to bin packing, then we know bin packing is NP hard. Okay. So those are 2 things we need to show. We need to show that bin packing is in NP, and we have to show that it's NP hard. So how can we argue that bin packing is in NP? We have to show that it's efficiently verifiable, right? So what is the answer that we can verify? Any ideas? Like, remember, we need to construct an algorithm that takes like some kind of witness, and that witness, for a correct answer, there should exist a witness that proves that it's a correct answer. And for an incorrect answer, that is an instance that cannot be bin packed into 2 bins, we have to show, like, for every possible witness, our algorithm will reject. All right, to verify a solution to bin packing, all we need to do is give as a witness the description of which elements are in which bins. And so our algorithm just has to check if every element is in at least one of the bins, right? Every element is in one of the bins, and both the bins sum to less than or equal to 1. Okay, and if there is a valid bin packing, then there's going to be, you can just give that to the algorithm and it will accept. But if there's no possible bin packing, then this algorithm will always reject, because it either won't describe a valid bin packing or it won't describe a bin packing at all. Okay, so that's the proof that partition is, bin packing is in NP. So now we have to show that it's NP hard. So we have to, in particular, show that partition reduces to bin packing. Okay, so how might we do this? Let me add an extra sheet. How might we show that? Remember, our goal, bin packing is NP hard. So the way we're going to do that is we're going to reduce partition to bin packing. And specifically, this is the bin packing for the k is equal to 2 case. Okay, so how do we show that? How do we show this reduction? Okay, well, let's make the following observation. So for partition, we're given a set S is equal to A1, AN, and we want to find a T such that the sum of the elements in T is equal to the sum of the elements not in T. Right? And if the sum of the elements in T is equal to the sum of the elements not in T, then the sum of everything, right? Or well, what is this sum equal to, right? This is the sum of the elements in T, this is the sum of the elements not in T, but the sum of everything must be the sum of the elements in the set. Is that right? So this is equal to just the sum I goes from 1 to n of a sub I. Okay? Any questions here? Oh yeah, it is divided by 2. Darn it, Smarty is 15 out of 15.
Let's go.
Okay, so yeah, really make sure you fill out this form. Okay? If you fill out this form and I can ascertain that you were here, you get Smarties, and the people who fill out the form on my Wednesday section will also get that as well. So I will have to do some math this weekend to figure out how much an Oreo costs. But basically, I'll ask you to just Venmo request me for 10 cents or something. Okay. All right. Congrats. So yeah, but this is divided by 2 though. Okay, because every element is in either S or T, or it's not in T. And so if the sums are equal, then the sum of both this and this is just the sum of everything in the set. So the sum of each individual one is just that divided by 2. Okay. So what do we want for BPO? For BP, I wrote it as BP. So for bin packing, we have S is equal to S1, Sn, and we want T1 and T2 such that what do we want? We want that the sum of I in T1 of S of I is less than or equal to 1, and the same thing for T2. I in T2 of S of I is less than or equal to 1. Okay, and let's call this Y, and let's call this X. Okay. Just for brevity. So is it possible, right? You might say let's just naively translate partition into bin packing. Is it possible for X and Y to be both less than or equal to 1, but not equal to each other? Like, can you imagine an instance of this? Well, sure you can. Like, if everything is much less than 1, then let's say we have the instance 0.1, 0.2, 0.3, then this, and then this, right? If we take these to be the 2 bins, they're both less than or equal to 1, but they're not equal to each other, right? Even though there are 2 elements whose sum equals, everything else in the set, right? So this would be a valid instance of partition, but it's not a valid instance of, or I mean, the bin packingness doesn't tell us anything about it, right? So how can we ensure that this inequality is when both of these inequalities are satisfied, that the sums equal to each other? And I'll give you a hint. You want to make this inequality, you want to make it tight. So basically, you want X and Y to not only be less than or equal to 1, but if there's a valid bin packing, you want them to be equal to 1. Okay? How can we make that happen? What should the sum of the elements in S be? Yeah. So what if we take X plus Y equals to 2? So we write this as a constraint set X plus Y is equal to 2. X is less than or equal to 1. Y is less than or equal to 1. So what satisfies this? So the constraint X is less than or equal to 1 looks something like this. The constraint Y is less than or equal to 1 looks something like this. Okay. Now, what about the constraint x plus y is equal to 2? That's like this line over here. Okay. And so this is the only point that satisfies all three constraints. And it's the point 1, 1. So if this is the case, if x plus y is equal to 2, x is less than or equal to 1, and y is less than or equal to 1, then x is equal to 1 and y is equal to 1. In particular, x equals y. Okay, so here's the idea. Maybe if we can convert the elements of partition into the elements of bin packing such that the sum of the elements in the bin packing problem is equal to 1 or is equal to 2, then maybe we can be onto something there. Okay, so in particular, let's say m is equal to the sum of the a sub I for I goes from 1 to n. Okay, so now try to think about the reduction from partition to bin packing. Okay, I'll give you a few minutes to think about that and let me know if you have any questions.
Or you could just turn EP into a follow-up partition. And then you can run it through
The question, okay, someone asked, why did we choose 1 as the bound? That is from the definition of bin packing. So remember in the bin packing problem, right, we have we want to place it into a small number of bins such that each bin like is at most 1 in total weight. Okay, so you don't want any of the bins to have more than weight 1, and so that's where we get the constraint. So bin packing basically has some items, and you have like you want to try to put them in as few bins as possible, such that none of the bins have their capacity exceeded. And in this version of the problem, we only have bins of capacity 1. Okay, so you can think about it as like, yeah, okay. All right, so do we have any ideas about how we can do this reduction? In particular, we have these a sub I. How can we define our s sub I in terms of them? Remember, we want the total sum of this s sub I to be equal to what? For the bin packing problem, what is the sum of the s sub I equal to? We want it to be equal to what? We want it to be equal to 2, right? So what do we take s sub I to be equal to in terms of a sub I? We know that the sum of the a sub I is equal to m, right? So s sub I is what in terms of a sub I? Look, the sum of the s sub I is equal to 2. The sum of the a sub I equals to m. So s sub I equals what in terms of the a sub I? Anyone? How about we can say something like this? S sub I is to 2 as a sub I is to m. Right? Notice if you sum both of these equations over I, you get 1. Right? So this is what we want S sub I to be equal to. So this means the S sub I, we're going to normalize it such that each S sub I is going to be proportional to A sub I, but we're going to normalize it such that the sum is equal to 2. Does this make sense? Any questions here?
Can you actually explain how you got that equation? S of I equals, yep.
Do you
Oh,
see
you
how
just
we got-
multiplied by 2. Yeah. Okay.
So S sub I over 2, right? So we want the sum of the S sub I to be equal to 2, and we want the sum of A sub I to be equal to M. So we'll say, okay, let's just let each S sub I be proportional to A sub I, and then renormalize it such that the sum is 2. Okay? And you can confirm that the sum of the S sub I is equal to 2 over M times the sum of the A sub I, which we determined was equal to M, which is equal to 2, which is exactly what we wanted. Okay?
Yep, thanks.
All right, so that's a reduction, okay? And we try to see if bin packing is possible here. Do we see why, if like bin packing is possible here, then the sum of the elements in T1 must be equal to the sum of the elements in T2? They must both be equal to 1, right? If one of them was greater than 1, then it would violate the capacity constraint, right? Do we see this? Okay, so now let's prove this reduction formally. So proof of reduction. It should be clear that this reduction takes polynomial time, right? Because for each element in the original problem, we're just scaling it by something. So it takes linear time and the number of constraints in the original problem, or the number of variables, okay? So what is the proof? We must first show if there is a partition, then there is a BP. Why is this? Well, there exists T such that the sum of the elements in T equal to the sum of the elements not in T. Okay? Right? So what do we take for our T1 and T2? This is going to be T1, and this is going to be T2. Okay? So what is the sum of the elements in T1 of S sub I? Well, it's the sum of the elements, it's 2 over M times the sum of the elements in T of A sub I, right? Because each A sub I is 2 over, each S sub I is 2 over M times A sub I, right? So I'm just doing the scaling from over here, and then I'm applying it to, I'm like using the fact that we're taking T1 and T to be the same set. So what, right? So what is the sum of the elements in T of A sub I? It's half of the elements in S, right? So it's M over 2. The sum is equal to M over, God dang it, I can't write today. What happened? Okay, the sum, this is M over 2. Do we see why it's M over 2? It's half of the elements. Every element is in either T1 or T2. So the sum of the elements in T1, oh, sorry, every element is either in T or it's not in T. And so the sum of like all the elements in T should be half of the sum of the elements in S. So this sum is M over 2, and so we get 1. Same thing for T2. Okay? So indeed, we have two bins, like we have 2 subsets that we can pack into these bins in this way. Okay? So how about we also have to show that if we can bin pack, then we can put it into partition. So the proof goes very similarly, right? If we can bin pack, then the sum of the S of I in T1 is equal to 1, and the sum of the Si in T2 is also equal to 1. Why is this? Because the sum of the elements equals 2, right? So the only solution that satisfies these three inequalities requires both subsets to be of sum 1. Okay. And that is, their sum is equal to 1, not the English word someone, but like their sum has. Okay, you get it. Okay, so so what do we do for our partition set? We just unscale these. Okay, so then we just take a sub I is equal to m over 2 times s sub I. So, oh yeah, and we take t is equal to t1. So the sum of t of a sub I is equal to sum not in t of a sub I, because their sum is both equal to 1. Okay. In fact, both of these sums are equal to m over 2. You can confirm that. All right. And so that is the proof. Any questions here? All right. So no questions? None? Okay.
Do you mind explaining that last part again real quick?
Yeah, sure.
But yeah, okay.
So we know that the sum of the elements in T1 is equal to 1 in this bin packing instance, and the sum of the elements in T2 is equal to 1. We know that if the bin packing instance is solved, then this must be the distribution, right? Because both the sums must be less than or equal to 1, and yet they must both add to 2. And the only way you can do that is if both of the sums are equal to 1. So now how do we find two subsets like that partition the set but are equal in sum? Well, we just take the exact same elements, like whatever the bins were for bin packing, those are going to be our two subsets for the partition problem. We just rescale them, right? So that they're integers, like we discussed earlier. Like I think partition requires it to be integers. The scaling is just a formality. We've already demonstrated two subsets here whose sum is equal. So therefore we can go from bin packing to partition. Does that make sense?
Yeah, thanks.
Okay, cool. All right, so now let's, any questions again? I'm gonna ask this one more time. Okay, so let's go on to proving hardness of approximation. All right, so our goal here is to prove that we can't find an approximation algorithm with ratio strictly less than 3/2 unless p is equal to np. Okay, so the idea is, like, if we have an algorithm that takes a bin packing instance and for every instance outputs a number of bins. So here we're not in the k is equal to 2. Can we fit into 2 bins? We're given a set of elements, each of which is less than or equal to 1 and greater than or equal to 0. We want to see what is the fewest number of bins we could put it in such that the sum of every bin is less than 1. Okay, does that make sense? So it's not a whether or not, it's a how many do we need. So we have to show that, you know, we can't do better than 3/2 in all instances. So how do we show this? Like, this is it's called a hardness of approximation result. Okay, so this is called hardness of approximation. If you take the graduate class on approximability, which is I think offered every fall, I'm in it right now. It's quite challenging, but you'll do things like hardness of approximation in general. But the question here is, right, unless p is equal to np, we want to prove that unless p is equal to np, there cannot exist an algorithm that does this. So how do we do it? We assume that there exists an algorithm that does it and show that that implies that p is equal to np. Okay, would you agree that would suffice? If there did exist such an algorithm, then p is equal to np, and so we can't do better than this unless p is equal to np. Okay, so how do you show that p is equal to np? What is one thing you can do to show that p is equal to np? Yeah, find a polynomial time algorithm for an NP complete problem. What is an NP complete problem here? Like, what sticks out to us here? This is a hardness of approximation result for bin packing. So what did we just show was NP complete? Partition, yes, but we also showed that bin packing was NP complete. Specifically bin packing in the case of 2 bins. Okay, so you need to argue that in particular, if there exists an algorithm that does 3/2 minus epsilon, so here epsilon is some number greater than 0. For everything, it always outputs something like less than or equal to 3/2 minus epsilon times the optimum. Then you solved an NP complete problem, and the NP complete problem you should try to solve is this problem. So the specific instance of bin packing where you can place your objects in 2 bins. Okay, so take some time and think about how you might solve this. Okay, so let's talk about this. All right. So we want to show that there exists an algorithm for 2 bin packing. If there exists an algorithm that does a 3/2 minus epsilon approximation algorithm. So what happens if we apply this approximation algorithm to an instance? So what happens if we apply the approximation algorithm to an instance of the bin packing problem where the optimum equals to 2? What are the possible number of bins we could return here? Could we return a solution with 1 bin? No, right? Because the optimum is 2. We have to do at least 2. So this algorithm could return something with 2, right? With 2 bins. It could return the optimum on some instances. Are there instances where it returns 3? What is the maximum that we can return? The maximum size number of bins that we return is 3/2 minus epsilon times the optimum, which is equal to, what is the optimum here? The optimum is 2, right? So the algorithm solution returns something. So the algorithm solution, it's greater than or equal to 2 because that's the optimum. The optimum is equal to 2. So this is equal to 3 minus epsilon. Actually, it's equal to 3 minus 2 times epsilon. Yes? Yep. But this is like less than 3. So we want to return something that is greater than or equal to 2, but less than 3. This algorithm can only be an integer, right? So what does this mean about the algorithm? What is the only possible choice for the algorithm to return? 2, right? This implies that the algo solution is equal to 2 in the case that optimum equals 2. Okay? In the case that the optimum is not equal to 2, that it's greater than or equal to 2, what do we return? We return at least that, right? So we notice that in this 2 bin packing problem, where our goal is to determine whether we can be packed into 2 bins or not, if the approximation, like if the optimum is less than or equal to 2, that is, it's a yes instance, then our approximation algorithm will return something with bin size with at most 2 bins, right? Why can't it return something with 3 bins? Because we didn't say 3/2 approximation algorithm. We said less than 3/2 approximation algorithm. So we can never return a 3 bin solution when 2 bin solution is optimum. Otherwise, we wouldn't be 3/2 minus epsilon. We'd be at least 3/2 for our approximation ratio. Okay. And in the case that there's a no instance, that is, we require at least 3 bins, well, then the algorithm will have to return something at least 3 as well. So if the algorithm returns something that's at most 2, then we can be packed in at most 2 bins, and vice versa. If we can be packed in at most 2 bins, the algorithm returns those 2 bins. Otherwise, it returns something with at least 3 bins. And so we know that the approximation algorithm will always solve this problem, okay, in the k equals 2 case. Any questions here? So this in particular implies a polytime algorithm for 2 bin packing. 2 bin packing we just proved in part 1 is NP complete. So this implies that P is equal to NP. Okay. Any questions about this?
Why does that imply that there's a polytime algorithm for 2 bin packing?
Remember, the 2 bin packing problem is, can we be packed in 2 bins? Return yes. Can we not be packed in 2 bins? Return no. What is our algorithm here? We run the approximation algorithm, and if it's less than or equal to 2, we output yes. If it's greater than or equal to, if it's greater than 2, we output no. Why does that work? Well, in the case that we can be packed in less than or equal to 2 bins, the algorithm will never output something that is greater than 2. That's because this approximation ratio means that we are, at most 3/2. We're in fact less than 3/2 times the optimum. So the output of the algorithm has to be less than 3. So it's always equal to 2. Does that make sense?
Mm-hmm. Yeah. Yeah.
Okay. And so we just use that algorithm and we can output the yes or no answer. Okay.
Okay.
All right. And we see how that implies P is equal to NP, because bin packing is NP hard. So this implies that P is equal to NP. So unless P is equal to NP, there's no algorithm for this problem with approximation ratio better than 3/2 minus epsilon. We haven't ruled out a 3/2 approximation algorithm though. It could still be possible to do it 3/2. We specifically use the fact that, we have this 3 minus 2 epsilon for epsilon greater than 0. Okay, so it's strictly less than 3. And that's why we never, in the yes case, we never output a 3 bin solution. Okay. So now for this last couple of minutes, like a section, maybe let's say I can go like 10 minutes. So what do you want me to talk about? So on Wednesday's discussion, which is uploaded, I talked a little bit about computability. What topic would you like me to go over for the exam? I'm trying my best to do that in 10 minutes. Any ideas? You can put it in chat if you have an idea. I'll wait patiently until I have a good idea. Like Turing, yeah. So a little bit about Turing machines, a little bit about computability. Do you want me to talk about that? Would you also like me to talk about that? Okay. So yeah, so what exactly do you want me to talk about, right? So with automata, right? It's like you just pretty much you follow like the rules of the automata. So I guess the confusing topic might be computability. So the halting problem, why like the halting problem, right, is it asks the question, does the Turing machine or does the program, Turing machines programs can be used interchangeably, does program P stop on input X, or well, I should say halt on input X, or does it the alternative, of course, is it loops infinitely. And so this is an uncomputable problem. There is no Turing machine that solves this on every input and also like terminates. Okay, and intuitively this is because like there's no general way to like understand the operation of a Turing machine or a program P without, you have to simulate it, right? So what if it's the case that P doesn't halt on input X? Well, you have to run it, you know, and you could get in an infinite loop yourself. And your question might be like, oh, just run it like for a really large number of times, and if it doesn't halt yet, then it's probably in an infinite loop. And this might work practically, right? Like if you like loop way more than you want to when you're writing a Java program, maybe something is going on over here. However, what's to say that this program just doesn't take a really long time to run, but it's still finite and not like an infinite thing? And so there's no real way to tell those two apart. And that's the intuition behind this. Now, why is it useful to have a program that like you know is uncomputable? Well, you can then design then you can prove that other programs are also not computable. So consider the following problem. So we'll call it print. We have program P and an input X. Does program P print, what should it print? Oreo on input X. So we're going to execute program P on input X, and we want to see if it ever prints the statement Oreo at any point. Okay, so is this uncomputable? And it turns out yes. And why is it uncomputable? Well, it's uncomputable because consider the following program. Okay, we'll say Q of Px. What it does is we're going to run P, but we're going to suppress the print statements. That is, we're not going to print anything, okay? And then print Oreo. Okay? So what happens if P of X halts? If P of X halts, does Q of X print Oreo? Yes, right? So if P of X halts, then this first line will finish executing and then we'll print Oreo. Now, if P of X loops infinitely, this Oreo never gets printed because we're stuck on this line of execution the whole time. Okay? So then all we need to do to define a halting function, assuming that print exists, we can just define halt as follows. Assuming that print is computable, then all we have to do is see if Q prints on the input P comma X. If Q prints Oreo on the input P comma X, that means P of X has halted. Otherwise, it does not. Okay? And this is kind of like an argument by the contrapositive. If this print existed, if this print was computable, that would imply halting was computable by this reduction over here. However, we know for a fact that halting is uncomputable, so therefore print must also be uncomputable. Does that make sense? Okay. Is there anything more you wanted me to say about this? I could try to explain why halting is uncomputable, but I don't want to break your minds. Like it is like really like mind bending to understand why. I mean, I could talk about it if you wanted, but what do you want me to talk about? Anyone have a suggestion?
So this was like not the proof for why the halt problem.
Yeah, it's not the proof.
Okay. See, whenever the proof in class, but I was a little bit.
Yeah, I don't understand the phrase at all.
Do you want me to explain that? I can explain it. Okay, so, all right, grab your seatbelts. So the way you do things is, again, okay, so the theorem is halt is uncomputable. The proof is, we're going to define the following program Turing. We'll call it Turing of P. And the key idea here, okay, this is something that you need to convince yourself of or just accept. Programs themselves are like strings. You can encode, like, this makes sense. Like, this should make sense. Anyone who is like coded should understand, because you can store programs as text files, and you just need some kind of language to interpret them. Okay, so programs themselves can be thought of as strings, and in particular, they can be thought of as inputs. So Turing of P, what is Turing of P going to do? Well, we're going to think of P as an input to itself. Okay, just accept that for now. But we're going to run the halting program. So we're going to assume that halt is computable. What does it mean for halt to be computable? Well, we can use it as a sub procedure. So assume that halt is computable. If halt of P comma P equals true, P of P halts. Okay, if P of P halts, then loop forever. If or else, so what happens if, so what is this else case? Else what? Else halt. So finish executing. So this else case is P of P loops. Okay, do we see what this is doing? We're taking the input to a program. We're taking as our input a program, and we're feeding that program as an input to itself in some bizarre way. Okay, just accept that that works, because programs are themselves strings. If on execution this program loops forever, then Turing of that program is going to halt. It's going to do the opposite of whatever that program is doing on itself. Okay, do you understand the construction of this Turing thing? It's doing the opposite of whatever, like Turing of P does the opposite of whatever P does on itself. So this is P of P, and the Turing of P does the opposite. How do we derive a contradiction here? What should we choose for P? What if we chose, and hang on with me here, okay? What if we chose Turing itself? I promise you I'm completely sober. So, but we'll choose Turing itself. Okay? So what does Turing of Turing do? Well, if Turing of Turing halts, right? So here P should be replaced with Turing. If Turing of Turing halts, then Turing of Turing will loop forever. Yeah, exactly. And wait, it does not make sense in a contradiction kind of way, or just okay, good, okay. Otherwise, that would be sad. But if Turing of Turing, if we're in this else case, what does that mean? That means Turing of Turing loops, but then that would mean that Turing of Turing would also halt. Okay. It's kind of whack. I know, but I think thankfully this is on the recording, so you can just like watch it over and over again. Okay, but don't enter an infinite loop when you're watching. Study other things. So this is not too important, but like classically, this is a was a major result that just kickstarted the field of computability theory. And no one really works on that anymore, but you should look at this as a founding of like, this is pretty similar to what complexity is like. This is a proof that there exists a program that is uncomputable. That's not an obvious fact by any means. Just like it's not an obvious fact that there exists a problem that all problems in NP reduce to. So HALT should be like 3SAT. We know that there's a program that's uncomputable. So now we can use that fact to prove by contraposition that there are other programs that are uncomputable. In particular, if we can use those programs as subroutines to solve the halting problem, then that's a contradiction. So those programs must be uncomputable. Okay, so this is again like a microcosm, or not a micro, it's just another example of how reductions are used in computer science. And if I've interested you enough, then hopefully you can like email me to find out more about like theory and stuff, and I'd be more than happy to talk to you about it. But are there any questions?
So this Turing program takes a program input, you call that program on itself. If it's supposed to halt, Turing is going to infinite loop.
Yes.
And so then you call Turing on itself. So
Yes.
basically it just does the opposite.
Exactly. Turing of P does the opposite of whatever P does on itself. So Turing of Turing does the opposite of whatever Turing of Turing does, which makes no sense. Okay. Yep. And how do we build Turing? Using the halting program. And so if that's the case, then it must be, it can't be a computable program. Okay. So yeah, are there any other questions? Well, if they're not, best of luck on the exam and for everything that follows. And thank you all for being a great section. So remember to fill out the Smarties form if you were here, and I'll make sure to, do the math and get you your 10 cents or whatever you want. Okay, so see y'all.